Good morning, students. Welcome to the class again. We were discussing carbon-13 NMR spectroscopy. Now we will see proton-coupled carbon-13. As we know, the spin-spin coupling occurs between two nuclei of which are having same nuclear spin. In this case, carbon-13 is having a nuclear spin of half, proton is also having a nuclear spin of half. That means there is a possibility for coupling between carbon-13 and protons. But you may raise a doubt, if it is possible, we also get carbon-13 and proton coupling in proton NMR, right? But in proton NMR, we don't observe this. Why? Why? Because the availability of carbon-13 is very, very less. Availability of carbon-13 is very, very less, just 1.14, 1.1%. So with that very mild availability, we may not observe any carbon-13 proton coupling. But in the case of carbon-13 spectra, we are studying carbon-13 spectra and we have plenty of protons in the molecule. So it is an obvious case that there will be a coupling between carbon and protons. They will follow because the nuclear spin. So this coupling follows the rule n plus 1. We don't need to use 2n I plus 1 because n I value is half. So 2 into half it becomes 1. So we can directly use the n plus 1 rule to predict the splitting of carbon-13 signals. We will take one example and see how we will have some coupling. Ethyl phenyl acetate. Ethyl phenyl acetate. In this, the carbonyl will get highest delta value around 180, 160 or 170. Then aromatic carbons will have highest delta value 1, 2, 3, 4, 5, 6. But because it is a symmetrical molecule, we do observe only 4 signals for aromatic ring. 1, 2, 3, 4 only. 2 and 6 carbons are chemically equivalent. 3 and 4 carbons are chemically equivalent. So we will observe only one signal for 2 and 6. Similarly, one signal for 3 and 5. Now we also observe carbon-13 signals for this CH2 because it is directly attached to oxygen. Next one will be this. So we have 4 signals here. So A, B, C, D, E. Then F will be this, G, and it is the least one. Right. I'll try to draw the modal spectrum. This is the carbonyl peak. Then we have aromatic peaks. Carbonyl carbon doesn't have any protons, so we don't expect any coupling. So it will appear as a singlet. Whereas this aromatic carbon, it doesn't have any protons, so it appears as a singlet. Whereas these 2 and 6 carbons, they have one proton, so 1 plus 1, 2. So it appears as a doublet. Similarly, these 3 and 5 carbons, they also have a proton, so they also appear as a doublet. They also appear as a doublet. And finally, this proton, this carbon, para carbon, this is also having a proton, so it also appears as a doublet. Now, next one is CH2 because it is having 2 protons, 2 plus 1, 3, so it appears as a triplet. It appears as a triplet. Then this is also having 2 protons, so it appears as a triplet. This carbon, it is having 3 protons on it, so it appears as a quartet. Remember, we do observe only one bond coupling. We do observe only one bond coupling, direct coupling. Okay, we cannot observe coupling due to the protons present on alpha carbon. Okay, right. We observe only coupling due to the protons which are present on the direct carbon. Now it is proton coupled spectrum. It is proton coupled spectrum, but it gives, sometimes it gives good information. That means it gives the number of protons present on the carbon, but sometimes it gives it looks very clumsy. See, if they are very close together, for because I am writing the spectrum, I am drawing the spectrum, I am drawing these peaks with a distance to give you some clear information. But in the spectrum, in the original spectrum, they may not be separated with this much distances. They may appear very close together. So in that case, it becomes difficult for us to identify the actual signal and the multiplet. So for simplicity, what we will do, we will decouple them. We will decouple the decoupled we will decouple all the spin couplings due to proton. So doesn't matter how many protons are there on the carbon, but it gives only as a singlet. So in this case, it gives a singlet. This is a singlet. Whereas this aromatic carbon, which is having having a proton, now it also appears as a singlet. This doublet also appears as a singlet. This doublet also appears as a singlet. This triplet also appears as a singlet. Triplet, singlet, quartet also singlet. That means when we take the decoupled spectra, what is happening? All the carbons are giving singlets. All the signals are becoming singlets. Then it is easy for us to identify the number of signals that are arising from the compound. Okay, then it is easy for us. This is for C double bond O. These four are for aromatic. These three are for 2 methylene and 1 methyl carbon. So then we can easily understand the carbon skeleton here, right? So most of the time we will study decoupled spectra. We don't study proton coupled spectra in carbon 13. So for this purpose, what we will have a decoupler in the instrument. What is this decoupler? It is again an energy source where we use a very high energy that is used to irradiate all the protons. When we irradiate all the protons with very high energy, their spin levels will be saturated. What will happen? The protons will be saturated. As we know, when they are saturated, we don't get any signal from them or any coupling from them, right? So when we want to get the proton decoupled carbon 13 spectra, we will use another energy source where we will irradiate all the protons in the molecule with a very high energy, so that all the protons become saturated and they don't interact with any carbon. So that second energy source is called as decoupler. So what we are using RF waves only. Okay, so we for measuring the carbon 13, for processing the carbon 13 decoupled spectra, proton decoupled carbon 13 spectra, we will have one more energy source, that is what is called decoupler in the instrument. We will look at one more example, N-propanol. Because this methylene carbon is attached to oxygen, we will observe a large delta value for this, next large delta, next large delta. Generally this appears between 30 to 60. This will be between 20 to 50. This will be between from 10 to 30, something like this, right? So in the carbon 13 spectra, we observe three signals. As I said, we will observe only singlets. So this is for A, B and C. And apart from this, we are also observing a triplet with 1:1:1 ratio, intensity ratio at 77 ppm. Generally, the middle peak will be at 77 ppm. So these three triplet with 1:1:1 intensity ratio, it is for the carbon from the solvent. What is the solvent? We use CdCl3 as the solvent for NMR experiments. It is the general solvent. We generally use deuterated solvents. We generally use deuterated solvents for NMR. So whatever the solvent we use, it should be deuterated. Why should we use deuterated? Deuterated solvents are used because deuterium resonance signals are used as a lock signal, or it also used as a reference signal, so that they'll keep the magnets and electronics adjusted correctly. So deuterium helps in adjusting the electronics and magnets. So we always use deuterated solvents in the NMR technique. And not only that, deuterium has a separate resonance frequency. It will not match with carbon, or it will not match with proton. Because it is having a separate frequency, it will not interfere. The signals of deuterium will not interfere with the carbon-13 spectra or proton NMR spectra. So that is why we use deuterated signals. Right. Now we will look at the solvents which we use in the proton NMR carbon-13, and how they are, where they will appear with what ratios. CdCl3 will not appear in proton NMR because it doesn't have any protons, but it appears in carbon-13 because it is having a carbon. Now the deuterium, whose mass is 1, its nuclear spin quantum number is 1. Nuclear spin quantum number is 1. So in this case, we must use 2I+1 formula to indicate the number of spin states. So total number of spin states. So 2I+1. So the total number is 3. That means deuterium is having 3 spin states. They are -1, 0, +1. Deuterium is having 3 spin states. So they are -1, 0, +1. Now, because it is giving a triplet in the spectra. How it is giving a triplet? For calculating the triplet, we must use 2Ni+1 formula. This is for multiplicity, right? This formula is for multiplicity. This formula is for total number of spin states. Total number of spin states. Don't confuse with both these formulas. Now, one deuterium is there, 2 into 1, and its spin quantum number is 1 plus 1. So 2 plus 1, 3. So it gives a triplet. So according to this multiplicity formula, it gives a triplet. Now the intensity ratio, it is different from proton NMR. For proton NMR, intensity ratios exactly follow the Pascal triangle, whereas for carbon-13 it doesn't follow the Pascal triangle. Here it will have different intensity ratios that I will give. For CdCl3, the ratio of 3 signals is 1:1:1. Because of its characteristic peak, we can also use CdCl3 as a reference in carbon-13 NMR spectroscopy. We don't need to use TMS also, because it gives a peak of triplet at 77 ppm. We can give that 77 value to this triplet, so that all other delta values will be adjusted accordingly. So CdCl3 can be used as a reference in the carbon-13 NMR. Here the coupling constant is generally between 45 Hz, coupling constant value is 45 Hz, and the chemical shift difference is 0.6 ppm in a 75 megahertz on a 75 megahertz instrument. So delta difference between the peaks is 0.6 ppm and 0.6 into 75. The coupling constant is 45 Hz. Generally, we observe very large coupling constants for carbon 13. Now, we will look at the splitting tree or intensity tree for carbon 13. For carbon 13, sorry, 2Ni plus 1 lines and intensities. If we don't have any coupling or interacting spins, we will get only one line, intensity is 1. If we have one coupling atom, we will have, that means one deuterium, we will have 3 signals. The intensity ratio is 1:1. When we have 2 deuteriums, 2 into 1, 2 into 2 into 1, so that means 4 plus 1, 5 signals. The intensity ratio is 1:2 is to 3 is to 2 is to 1. When we have 3 signals, 2 into when we have 3 deuterium atoms, 2 into 3 into 1, 6 plus 1, 7 lines. So we will observe 7 lines. For 7 lines, the intensity ratio is 1:3:6:7, then repeat 6:3:1. For 4 deuteriums, we will have 9 peaks, 1, 4, 10, 16, 19, then repeat 16, 10, 4, 1. For 5, we will have 11 peaks, 1, 5, 15, 30, 45, 51, and then repeats 45, 30, 15. For 6, we have 13 peaks, 1, 6, 21, 50, 90, 126, 141, and then repeats. We may not need to remember all these values, at least remember up to this. These are intensities for a deuterated multiplet. We also use deuterated DMSO, dimethyl sulfoxide. It is called DMSO D6. DMSO D6. We have 6 deuterium atoms. It is a more polar solvent. So compounds which are not soluble in CdCl3, if some compounds are not soluble, then we will go for DMSO, generally for carboxylic acids. Because we have 3 deuteriums on carbon, so according to 2Ni plus 1 formula, it gives a septet. With ratios 1:3:6:7:6:3:1. So it gives a septet 1, 2, 3, 4, 5, 6, 7. Here the coupling constant value is 40 Hz, and it appears at a delta value, that means the middle peak, it appears at a delta value of 39.5 ppm. So the carbon in DMSO D6, because these two are chemically equivalent, these two carbons will give only one signal. So that will appear as a septet at 39.5 ppm. Now we will look at the intensities, how they are giving different intensity ratios. For example, if we have one deuterium on the carbon, then it will have, according to 2ni plus 1 rule, it will have 3 signals, right? Now, how do we adjust these nuclear spin values? For deuterium, it is nuclear spin is I is equal to 1, so it will have a total of 3 spin states. What is that? -1, 0, 1. Then how do we get these things? Okay, right. We need to have a +1 for this, we need to have a 0 for this, we need to have a -1 for this. So upward arrow represents +1, downward arrow represents -1, and it is 0. So we can arrange these 3 spin states, +1 one time and 0, I will use a dot to represent the 0 spin state, and we can use -1 here. So the 3 signals are arising because of 3 spin states. There is equal possibility. Nucleus can be in -1 state, it can be in 0 state, it can be in 1 state with equal possibility. So we will get a ratio of 1:1:1 for the triplet. Now we will look at the CD2. If we have 2 deuterated deuteriums on carbon, according to 2ni plus 1 formula, it will give 2 into 2 plus 1, 5. It gives a quintet. Now, how do we arrange them? These 3 spin states, yeah, when we have 5, then the spin states will be -2, -1, 0, 1, 2. The 5 possibilities are +2, +1, 0, -1, -2. Now we need to adjust these spin states so that we should get a total value of this. For example, how do we get +2? When we have 2 positive spins. That means when nucleus present in the +1 state, 2 nucleus present in the +1 state. So +1 +1, it becomes +2. This is the only possibility. How do we get +1 state? If we have a +1 state and 0 state, or 0 state and +1 state, that means there are 2 possibilities. Here this is the only possibility, so 1:2. Here there are 2 possibilities, so 2:2. Then how do we get 0? We get 0 if the nucleus is in 0 state, this is one possibility, or if the nucleus is in +1 state and -1 state, or reverse, -1 state and +1 state. That means there are 3 possibilities. So the ratio is 1:2:3. How do we get -1? For -1 also there are 2 possibilities. If the nucleus is present in -1 state and 0 state, or 0 state and -1 state, we have 2 possibilities. And for -2, there is only one possibility, if it presents in 2 -1 states. There is only one possibility. So by adjusting these 3 spin states into the total number of possible multiplets, so we can identify the intensity ratios. So here the quintet will appear as 1:2, 2:2, 3:2, 2:1 ratio. 1:2, 2:2, 3:2, 1:1, sorry, 1 ratio. So this is how we need to identify the intensity ratios for carbon signals when deuterium is present on them. Now we will look at acetone D6. Acetone D6 is again an NMR solvent where we will deuterate the 6 protons with deuterium. Of course, we know for a D3 system, CD3 system, we will get 3 into 2, 6 plus 1, 7 septet. For this carbonyl, we will get a singlet. For carbonyl, we will get a singlet. Then for CD3, we will get a septate. 4, 5, 6, 7. Generally, we will get 206 ppm for ketone, and for acetone D6, the methyl appears at 29.8 ppm. It is singlet, it is septate. It is septate. For acetone D5, now we will look at acetone D5. That means after long standing, it may decompose so that one of the deuterium is exchanged with proton. Then it becomes acetone D5. CD3, CO, CD2H. So it may be present as an impurity because we don't buy this acetone D5, okay? But we will buy acetone D6, but after long standing, it may decompose to give acetone D5, which is an impurity. Then how do we identify this as an impurity? When we use the acetone D5 in the proton NMR, because we have a proton, it appears in the proton NMR and it gives a quintet. It gives a quintet because of the coupling between proton and deuterium. Because of the coupling between proton and deuterium, it gives a quintet. It appears at 1, 2, 3, 4, 5. It appears at 2.07 ppm in proton NMR. In proton NMR. But in carbon 13, how it appears? In carbon 13 NMR, CD3, it's not a problem. We will get a septate. But for CD2 and H, we have two different nuclei. Then how do we find the multiplicity? For D, we will use the formula 2Ni plus 1 multiplied by, for hydrogen also we will use the formula 2Ni plus 1. This is for deuterium, this is for hydrogen. For deuterium, we have two nuclei and its nuclear spin is 1 plus 1. For proton, we have only one proton and its nuclear spin is of plus 1. So a total of 2 into 2, 4 plus 1, 5 into 1 plus 1, 2. So we will get 10 signals. For CD2H, we will get 10 signals. So this is how we calculate the multiplicity when we have two different coupling atoms. Okay, we will calculate the multiplet for each type of atom, for deuterium and for proton, and we will multiply them. So you can add on if you have more number of coupling units, coupling atoms. Sometimes it is possible that we may not observe these 10 signals. They may overlap with CD3. We have CD3 one side, CD2 one side. So sometimes we may not observe these 10 signals. They may couple with CD10 signal also. So they may overlap. They may overlap with this.